Now, let's focus on this special feature of this particular model that I discussed a little bit earlier. Think of the event heads in the second toss. If I tell initially the probability of heads in the second toss, you know that it's P, the probability of success of your coin. If I tell you that the first toss resulted in heads, what's the probability that the second toss is heads? It's again P. If I tell you that the first toss was tails, what's the probability that the second toss is heads? It's again P. So whether I tell you the result of the first toss or I don't tell you, it doesn't really make any difference to you. You will always say the probability of heads in the second toss is going to be P, no matter what happened in the first toss. This is a special situation to which we're going to give a name, and we're going to call that property independence. Basically, independence between two things stands for the fact that the first thing, whether it occurred or not, doesn't give you any information, does not cause you to change your beliefs about the second event. This is the intuition. Let's try to translate this into mathematics. We have two events, and we're going to say that they're independent if your initial beliefs about B are not going to change if I tell you that A occurred. So you believe something, how likely B is. Then somebody comes and tells you, you know A has happened. Are you going to change your beliefs? No, I'm not going to change them. Whenever you are in such a situation, then you say that the two events are independent. Intuitively, the fact that A occurred does not convey any information to you about the likelihood of event B. The information that A provides is not useful, is not relevant. A has to do with something else. It's not useful for your guessing whether B is going to occur or not. So we can take this as a first attempt into a definition of independence. Now, remember that we have this property. The probability of two things happening is the probability of the first times the conditional probability of the second. If we have independence, this conditional probability is the same as the unconditional probability. So if we have independence according to that definition, we get this property that you can find the probability of two things happening by just multiplying their individual probabilities. Probability of heads in the first toss is 1/2. Probability of heads in the second toss is 1/2. Probability of heads is 1/4. That's what happens if your two tosses are independent of each other. So this property here is a consequence of this definition, but it's actually nicer, better, simpler, cleaner, more beautiful to take this as our definition instead of that one. Are the two definitions equivalent? Well, they're almost the same, except for one thing. Conditional probabilities are only defined if you condition on an event that has positive probability. So this definition would be limited to cases where event A has positive probability, whereas this definition is something that you can write down always. We will say that two events are independent if and only if their probability of happening simultaneously is equal to the product of their two individual probabilities. And in particular, we can have events of 0 probability. There's nothing wrong with that. If A has 0 probability, then A intersection B will also have 0 probability because it's an even smaller event. And so we're going to get 0 equal to 0. Corollary of what I just said, if an event A has 0 probability, it's actually independent of any other event in our model, because we're going to get 0 equals to 0, and the definition is going to be satisfied.